go a little faster this time. Step 1 from the last video was to bring everything to one side. So x squared minus 2x minus 1 is greater than 0. Step 2 is to highlight what we're finding. We are finding things that are greater than 0. So I am looking for the positive sections of my sine array. I am looking for above the x-axis. Step 3 is to factor. So this is my easier method of factoring. I don't have anything in front of the x squared, so I just need to multiply to the negative 1 and add to the negative 2. When I think about that, nothing multiplies to negative 1 and adds to negative 2. So factoring doesn't work, which means we're going to have to use the quadratic formula as our backup plan. So I have negative b plus or minus square root of b squared minus 4ac all over 2a. And the nice thing about the quadratic formula is step 4 in our process of this was once we have it factored, we set each factor equal to 0 and solve for the x-intercepts. That was step 4, the x-intercepts. Well, you'll notice the start of the quadratic formula is x equals. So this quadratic formula is actually finding your x-intercepts. These answers will be your x-intercepts. So if I simplify this down, I get that. And I can simplify this further by factoring 8 to 2 times 4, and 4 is 2 times 2. Circle my pair of 2's and take them out, and I have 1, 2 left inside. And then I can divide both parts of the numerator by the denominator. So I divided that by 2 and that by 2, which simplifies to 1 plus or minus root 2. So these are my x-intercepts, 1 plus root 2, 1 minus root 2. So step 5 was to make our sine array. On our sine array, we start with our number line. 1 minus root 2 is going to be less than 1 plus root 2, because subtracting is always less than minusing. Subtracting moves you farther to the left on the number line. Then I list those up here as our x-intercepts on the side. And then they each get their own number line. So for this number line, this is my 1 minus root 2 line. So my 0 is going to go above my 1 minus root 2. So 0, to the left of the 0 is negative, to the right of the 0 is positive. Here's this number line, that's my 1 plus root 2, so it's going to have a 0 above 1 plus root 2. Left is negative, right is positive, and now I look at my columns. 2 negatives makes a positive and a negative make a negative, and 2 positives make a positive. You may notice this just happens to be the same pattern as the last example we did. That is totally coincidence. That doesn't usually happen very often. So we have this pattern. We go back to what we highlighted. We wanted everything greater than 0 or our positive sections. So I wanted that section and that section. Those are my greater than 0 or my positive sections. So this is going to go from negative infinity up to 1 minus root 2. Use parentheses because it's not equal to. Union, this section is going to go from 1 plus root 2 up to infinity, parentheses because we're not equal to. And those are the sections of my graph that will be positive or above the x-axis. Now, 2 words of wisdom about sine arrays before we move on. First off, sine arrays can be very fast. They're a wonderful shortcut. However, word of warning, do not get lazy with them. If you let yourself get lazy with them and start skipping steps, it is very easy to make little mistakes that ruin the whole sine array. So let me give you an example. A common one I see is that students will not write the stuff on the side. They just skip that step. They won't write that out. But then they forget where the 0 is supposed to go. because they don't have this title over here that says where the zero is supposed to go. So let's say I did that and I forgot that I was supposed to have a 0 on each one. So I have a 0 on this one, and let's say I made the mistake and accidentally put a 0 on both of those and did left is negative, right is positive. Now I would get that every section is positive, which is wrong. So that's why it's really important that you not skip any steps and you actually write out all the steps of your sine array. Don't let yourself get lazy with this, because that is where little mistakes happen. Second piece of word of wisdom for sine arrays. I'm going to go back to this problem. Let's say, so you know how in the English language, we have a lot of rules, and there are sometimes exceptions to those rules. There's like, this rule happens most of the time, but like 10% of the time it doesn't work. Well, that happens here with sine arrays. There's a small thing that occurs very rarely that you need to be careful of, and that is negative leading coefficients. If you have a negative leading coefficient anywhere in your problem, so let's say maybe, we'll do this in red so it's bright. Maybe you have a negative leading coefficient at the beginning up here. Or maybe when you factor this out, you get a negative leading coefficient down there. Whatever it is, if you have a negative leading coefficient, you must come to your sine line and do a row of negatives, because negative leading coefficients flip signs. It's kind of like distributing a negative. Distributing a negative changes all the signs. So if we have a line of negatives here, it's going to flip all of these signs. So that is something, it doesn't happen very often, but if you have a negative leading coefficient anywhere in your problem, you need a negative leading coefficient line of negatives, or else you'll mess up all the signs. So those are my two pieces of words of wisdom for sine arrays. Don't get lazy, write out every step. And two, if you have a negative leading coefficient, watch for that. Be careful with those and add your line of negatives. So that is what we've got so far. In the next video, we're going to talk about what to do with our sine arrays when we have multiple